Today, I'm going through the fed state. I'm going to start off with insulin regulation. So you have a pancreatic cell, specifically a beta cell, right? So beta is insulin. Think about beta insulin. Alpha glucagon. Okay? And on these cells, on these beta cells, you have GLUT2 transporters. Okay? And then we have glucose. Glucose comes in and is converted to G6 added phosphate, glucose 6 phosphate. And we use the enzyme hexokinase or glucokinase. Okay? Then we convert this to energy, ATP, a form of energy, eventually reaches energy. And this increase in ATP, there's potassium channels, triggers, so that's that would be step 1, this would be step 2, this I would consider step 3. It opens potassium channels, opens potassium channels that release potassium outside of the cell. And when you take potassium, a positive charge outside the cell, you're depolarizing the cell. So depolarization. Okay? We also have calcium channels. And when these calcium channels sense depolarization, they automatically open and calcium floods into the cell. Okay? And we've got calcium receptors inside the cell. And when they register that, insulin droplets contain insulin, vesicles that contain insulin, move to the plasma membrane and exocytose their contents. That's insulin regulation. Let's go to glycolysis. Glycolysis is the production, we want to try to generate energy, okay, from glucose when we eat. So I'm going to use G as glucose. We first add a phosphate, G6P, then we convert it to fructose, 6-phosphate. Then we add another phosphate, okay? Now where it gets different is we convert it to 3-glycerolaldehyde and DHAP, dihydroxyacetone phosphate, okay? I'm going to add these enzymes, now. This is hexokinase. Remember we saw that before in insulin regulation. Or glucokinase. This is phosphoglucoisomerase. Here's phosphofructokinase. Okay. Now I want to add, to get from here to here, use aldolase. Glycerolaldehyde 3-phosphate DHAP. Now they are interchangeable. They're converted back and forth. But what happens with the D3P is it's converted to 1,3-bisphosphoglycerate. Okay? And then this is then converted to 3-phosphoglycerate. Two phosphoglycerates then converted phosphoenolkinase, and then finally what we want, pyruvate. Let's fill in these enzymes while we're here. This enzyme here is called glycerol aldehyde 3-phosphate dehydrogenase. Okay? This enzyme here is called phosphoglycerokinase. This enzyme here is called phosphoglyceromutase. This enzyme here is called enolase. This enzyme here is called pyruvate kinase. Okay. Now we've got all the enzymes down. Let's work on now. I just want to work on what we're actually gaining from this, because remember, ATP is our energy source. So we lose an ATP here. So we remove a phosphate from ATP here. Remember, glucose 6-phosphate, and we lose another one here when we're adding another phosphate. That's 2 we've lost. So this is called energy investment. During this process, during glycolysis, we are investing 2 ATP to generate energy. That's the 2 ATP we do there. Okay? We also generate other things. When we convert fructose 1,6-bisphosphate to glyceraldehyde 3-phosphate, we generate NADH H+. Now mention NADH is an electron carrier. That will be used later in the electron transport chain. It equals roughly 2.5 ATP. Okay. Now, we generate ATP here at the end. We generate water here. We generate ATP here again. That's it. So this, I just want to mention now, we have 2 glycerol molecules, so this happens twice. So what happens is what? So we got 1 ATP here, 1 here, we've got 2 NADH here, so that's 2 ATP plus NADH, remember? And it's 2 reactions. So we have 4 ATP 4 ATP in total at the end of the reaction. However, we used 2 ATP to start with. So the net equals 2 ATP plus 2 NADH. So this is glycolysis, the breakdown of glucose. Okay? Good. Oh, sorry, no, I forgot to mention something. Well, I'm going to mention the rate limiting steps. So the most important steps. The reason is these steps regulate the whole glycolysis process, really. So this step here is non-reversible without an enzyme, right? Just want to mention that. This step here is another rate limiting step. It's non-reversible. And here's another rate limiting step. But that is reversible. Okay? Let's go over to glycogenesis. Okay. Glycogenesis, as the name suggests, genesis is the production. So we're producing glycogen from glucose. Okay? So we ought to start off with a glucose. Like usual, we add a phosphate and we use hexokinase. Or glucokinase. Then we rearrange it. So I just want to mention, so we've got glucose here. Let me draw up glucose for you. Got glucose here. What we've done here is all we've done is add a phosphate. Then we're going to rearrange it. We're going to put it here. So this is G1P, G6P, and this is glucose. Okay, so we rearranged it. And the enzyme that does this is phosphoglucomutase. Rearranges. Now we're going to remove the phosphate. And we're going to generate UDP glucose. So we're going to take away this phosphate, right? We're going to take it away. And what we're going to end up putting is UDP. And you're going to say, okay, how did you generate UDP? Okay, so in this step, what we've done is we've used UTP, right? And we have taken out, so from UTP, so we take off two phosphates. So now we take off two phosphates to produce UMP. So we add UMP. What we're doing is we're adding UMP to this. And we have the original phosphate. So UMP, so we're taking off two phosphates from the UTP that we're using. And we're adding UMP to that phosphate group on the glucose 1,6 phosphate. So we're adding UMP to this. And now we've got an extra phosphate, so it's called UDP. Uridine diphosphate. Okay? And you'll see why we want to add this. Now, so let me just add this enzyme. This enzyme, I'll just add it. I'll remove this. This enzyme is called UDP glucose pyrophosphorylase. That's what the enzyme's called. And now we want to generate glycogen. And I want you to remember glycogen is literally like just chains of glucose, right? Etc. It's chains of glucose, and it has branching. I'm going to add. So what we're going to do now was you're going to use an enzyme called glycogen synthase. And what that's going to do is it's going to get all these UDPs and join them together. So now we can join all these glucose residues. And we're going to use, so it will join them. And it's going to form a bond between them. And this bond is called 1,4-glycosidic bond. Okay? So it's going to keep on going to approximately, let's say, 11 residues. Okay, but that's not how glycogen is normally formed. Glycogen is usually branched. Okay, so glycogen would usually be something like this. It would actually have a branch and it will have more sets of glucose attached. And this bond is called 1,6-glycosidic. How are we going to generate? How are we going to generate these bonds? How are we going to generate 1,6-glycosidic? We have 1,4 and we have 11 residues. Well, we've got another enzyme called the branching enzyme. Final enzyme. And what this branching enzyme does is it will cleave off, so it will take off. So it will break off a bond. It will break off bonds, and then it will add them. So we'll add it, break the bonds, then reform it to form literally form it. So it's adding and forming one glycosidic bond. So it's taking off residues. So it's cutting some off and moving them. So it has transferase activity. So it's moving those enzymes. So it's branching them. So it's able to directly take off some of these. It's able to directly take off some of them, from not the whole chain, some of them, maybe 5 or 6. Take them off and then add them to that residue and form 1,6-glycosidic bond, as saw before. That's 1,6-glycosidic. Okay. I think that's it for today. Or